Welcome to the EECS 3215 Embedded Systems class on the Universal Asynchronous Receiver and Transmitter. This is another one of the classes on serial protocols, and this time we'll be covering the UART. So we'll talk about what the UART is, we'll talk about a related cousin called the USART, we'll talk about why we want to use it, some very simple examples of how it can be used, and then a little bit more complex ways of using it and getting messages to be transferred from your LPC802 onto your PC as an example of things that you possibly could do if you were setting up a GPS or some other device that needs to talk to your microcontroller. The LPC802 is a microcontroller that we use. It's from NXP. It has 4 serial interfaces. One is called SPI, one is I2C, and it has 2 UART or USART systems on board. We'll begin by having a discussion about what is serial communication in its absolute simplest form and generally what it's used for. All right, so what is serial communication? Well, basically it boils down to sending bits of information in ones and zeros, or 3 volts and 0 volts, or logic high and logic low, from one device to another device over a wire or a fiber or some other means. Each bit in this stream of information means something, but that meaning only comes about if we know something about the context of the transmission or context of the transmitting and receiving devices, as well as the sequence or order in which those bits are transmitted. So depending on sort of whether a 0 comes before a 1, or whether one device is a GPS system or a Bluetooth module or a temperature sensor, and what the microcontroller is, those things provide context in order for us to send a sequence of information, and which of those bits does what within that sequence will tell you what sort of message is being transferred between one device and the other. Probably the most visually striking representation of what serial information is the falling rain or digital rain in green and black that we find on different scenes in The Matrix, the movie from 1999, where you have these serial streams of information going from top to bottom with different letters and characters and numbers in them. And that sequence means something as part of the movie. All right, so those sequences can be pretty complicated, but we can also send really simple transmissions as well. They're not really full of meaning, but at least we can show that there's a transmission going on between your microcontroller and your computer. And sometimes when you're getting started, that's really where it's at. And so if you want to, you can send data from your microcontroller to a computer over 1 or 2 pins using GPIO or using a timer. And you can send really, really simple messages just to make sure that you've got a connection between the two. And when you're developing, that's often a really good idea. So today what we're going to show you in the first instance is a series of pulse width modulated bits, which is basically meaning the voltage goes up and down, up and down, up and down. Half the time it's on, half the time it's off. Half the time it's up, half the time it's down. And those bits that are going up and down are being sent from the microcontroller, and you can see the visualization within this logic analyzer where I was measuring the voltage coming out of the microcontroller. And then it's sent over, in this case, a USB line into a PC, right? So a PC with like a keyboard and a mouse or a trackpad. It's being sent over USB into the PC, and these up and down signals are being converted after you get a certain number of them into periods using a terminal program. Okay, and so basically what happens is that you've got these bits that are coming in. You can see them sort of 1 at a time, 2 at a time sort of thing being transferred. And if you get enough of these being transferred along your USB line, you get a single period appear. You can send more of them and you'll get another period, and so on and so forth, until eventually you send a whole whack of these and you get 5 or 6 or 7 of these periods appearing one after the other at a particular frequency. Now, the bits are being transferred at 50% duty cycle. That's why we call it pulse width modulation, because we're controlling the width of these pulses. So they're off half the time and on half the time. This is logic 1, that's logic 0. Or this is off and that's on. Okay? And we're transferring with a period from there to there of 3.3 milliseconds, or we say that we have a transfer frequency of 300 hertz. So one complete cycle of this signal, okay, which is one low and one high, is, or 2 bits basically is what's being transferred here, is being transferred at a frequency of 300 hertz. All right, so that's basic serial communication going on right there that you can actually test and visualize using your PC and your microcontroller. So what is a UART? A UART is a universal asynchronous receiver and transmitter. It does both transmission and reception, and it does so in an asynchronous or non-clocked, from an external perspective, method. All right, so on your microcontroller, your LPC802, you have a UART, which also has the possibility, this is sort of a modern thing, of synchronous transmission. And so this UART module has a possibility of requesting for transmissions, and it can get notices of reception of data. It can send packets of information. So actually the data, the sort of the meat and potatoes of what's going on inside of the messages, that can be between 7 and 8 bits long. You can control whether or not there's 1 or 2 stop bits. So these are bits that are sent at the end to say, we're done. There can be sort of a simplified method of error checking to make sure that the packets aren't bad. There's support for a simple networking interface called RS485, and there's a testing method as well that's built in called loopback testing. So what we're going to do now is we're going to send messages from the PC or to the PC via the UART on the microcontroller. All right, so the way we do that is we are going to take this microcontroller, we're going to send information from it into the debugger that's found on board the board. And then there's going to be the USB connection that takes that message that's transferred or transmitted or translated into USB format and sends it via USB to your PC. All right, so there's the USB, that's the LPC802. And if you want to test that signal, say using an oscilloscope or a logic analyzer, you can look at the transmit and receive pins that are found on the bottom header right over here. All right, so we're going to send pulse width modulated pulses to the PC's terminal program, and we're going to use a program like CoolTerm or RealTerm to do that. To set up this really simple version of a transmission system, we're going to use the wake up timer to have a nice timed signal. We're going to put a reload value of 1667 in it. We're going to use the low powered oscillator, which runs at 1 megahertz as the clocking signal for the wake up timer. And we're going to toggle the GPIO 4 pin, which is used to transmit data from the LPC802 to the debugger module, which is then transferred over to the USB line. All right, so once we set this up, we're just going to do configuration. Well, we're going to start with configuration, then we're going to go into the main loop in the main function, and we're going to do all the real work inside of an interrupt service routine. So the configuration for the wake up timer basically is to say that we need to have GPIO, and GPIO is going to be an output on, actually in this case, that wasn't supposed to be LED output. This is supposed to be TXD output. TXD, a little typo right there, because it's defined right here as TXD output right there. A little typo, I apologize for that. So we're going to take the TXD line and we're going to set it as direction output, and we're going to start off by clearing it, which makes it turned on. So it's not the LED instead, this is the TXD line. Okay. After that, we're going to turn on the wake up timer. We're going to turn on the clock to it, and we're going to disable the interrupt request from the wake up timer. We are going to select the low power oscillator for its clock. Okay, and then we're going to load the counter inside of the wake up timer with the reload value, which was 1667. Okay, and then we re-enable interrupt requests. All right, then we have an interrupt request handler, which basically clears the interrupt flag when it's achieved. It reloads the counter, and then it toggles the TXD output. There, that wasn't the typo. That's the proper one right there. It will toggle TXD output so that you end up getting up and down, up and down, up and down, which then gets transferred, if you get enough of these, into individual periods in your terminal program. All right. Now, all this is good for is to show that you can transfer information from your LPC802 into the terminal module or the terminal program on your PC. Now we got to actually try to do something useful. So rather than just sending periods like this, what we want to do is send like letters and symbols and things that actually have meaning. So in this case, we're going to do something just a little bit more complicated. We're going to send the letters A, B, C, D, and E. All right. So we want to be able to send A, B, C, D, E. And we have to be able to figure out a way of converting that idea into actual signals, up and down, on and off signals on the transmission line of the UART. So we're going to do that. Now, how do we do that? Well, one of the first things we need to do is set up a terminal program to accept a particular baud rate or bit rate that we're going to be transmitting at. So we can use clear term or real term for that. Sorry, cool term, not clear term. Anyway, so a little bit more detail here with respect to the UART. When we're setting this up, it's important to point out that the transmission from one device to another device doesn't, unlike something like SPI or I2C, doesn't have a clocking line or wire dedicated for sending a clocking pulse. So we do not have synchronization. We have to make an assumption about frequency, which basically means that the programmer who's programming the microcontroller needs to say, this is the transmission frequency. And the person who's writing the program or running the program on the PC needs to have read that somewhere and has to set up their program to receive at that particular frequency. All right. All right. And we've talked about the USART earlier. All right. So how do you set that up? Well, on a program like CoolTerm or RealTerm, you go into one of the menus and you say, this is the COM port that I'm going to be listening to. And that's generally found in your hardware configuration program, control panel, etc. And you select a frequency. It could be 9600 baud. It could be 300. It could be something really fast like 115,200. So you want to set how many bits per second it's going to be receiving at. Then you want to basically say that you want to either go really slow or you want to go really fast. If you're going to go really slow, the advantage for us in this case is that you can actually see the progression of letters that appear on the screen. But most of the time you want to go relatively fast. 9600 baud is a well-established frequency or baud rate for things like faxes. And for comparison, the fastest that you could go with a dial-up connection using regular phone lines back in the sort of early 2000s was 115,000 baud. All right. So when we set all of this up, what we need to do and take into consideration is that we need to take a really fast clock that we have internally in the microcontroller, which is often a megahertz or 9 megahertz or 15 megahertz or 600 megahertz. And we need to bring that down. We have to throttle it down. And we have to choose some combination of factors that scale down that initial frequency into something that's actually usable to transmit data. You can't actually go to any arbitrary speed on your wires. There are reasons for why that's not possible. So you have to be careful about what frequencies you end up choosing. Anyways, in order to configure that, there are on the LPC802 5 variables that need to be taken into consideration. First is the main clock source. In our case, that's normally 9, 12, or 15 megahertz. In our case, we're going to be using 12 megahertz. Then there's prescale values or registers. There's a multiplication one, there's a dividing one, then there's another register called the baud rate generator, which has another number in it, and then there's another register called the oversampling register. And each one of these has a different meaning and a different reason for its existence, but basically they're all going to be brought together into a single equation, and you need to search out these 5 values in order to get the end result, which is the rate at which you want to actually transmit data. Some restrictions are important to point out, or some things that are important about these individual registers. For instance, the oversampling register, or the OSR, should typically be about 16. That's the recommended value for it. Don't worry about why that's the case for right now. By default, 16 is fine. You set it to F, which is 15, and 1 is added internally inside of the hardware to it. So you just set it to 15, and the LPC802 hardware will add another 1 to it to make it 16. And it's just important to know that because it factors into the calculations that you make. The divider, for whatever reason, probably some reason with respect to the architecture of the LPC802 and maybe other devices within the family. In the case of the 802, we can only set the divider register to 256, which is its default. The multiplication register, on the other hand, can be set between 1 and 255, and the baud rate register or generator register can be set between 1 and 65,535. So this still is a large search space. So you have 5 variables, and some of them are constrained a lot, but it's still a large search space. And so generally you want to be able to write an algorithm or have a table that you can look up values in order to know which values of BRG, mult, OSR, div, etc., or even your FRO that you should use. The equation for doing this is basically your input frequency, like 12 megahertz, divided by 1 plus the multiplication register, divided by the dividing register, multiplied by 1 plus the OSR, the oversampling register, and multiplied by, on the divisor, 1 plus the baud rate generator. Okay. I wrote a MATLAB search script in order to figure out what the actual baud rate would be if I took these variables and popped them all in for different values of input frequency, multiplication, etc. That search script looks like this, where I set 12 megahertz. My multiplication register value is an array. Div is a particular value, my OSR is that, etc., etc. And what I'm trying to do is minimize my error. Okay, so the error is the difference between my desired baud rate and, based on this equation, the actual baud rate that is achievable using the distinct values that there are for things like frequency, multiplication, divisor, etc., or dividing, etc. Okay, you run that script a bunch of times, and eventually you can populate a table. And the table, well, I set up 3 tables, in fact. One for a main frequency of 9 megahertz, one for 12 megahertz, and one for 15 megahertz, where each row is a particular baud rate, so 300 all the way up to 115,200. Now, what's important to point out here is that while you can choose different values of your multiplier and your baud rate generator, different combinations will result in different values of baud rate error. So, for instance, if I put in a multiplication register value of 244 and a BRG of 959 at 9 megahertz, I will get exactly 300 baud with no error. So my desired and my actual resulting baud rate will be exactly the same. That's great. And a lot of the time, this isn't a big deal if there's a little bit of error, but in some cases with some devices, there's an expectation of exactly precisely the baud rate that it is that is intended. In any case, for 300
baud at these particular values, I get 0 error. Now, if I wanted to go really fast, I wanted to get up to 115 kilobaud, and I ended up taking only the values that gave me the minimum amount of error. At 115 kilobaud, I will have a baud rate error of 92 baud. Now, if the receiving device can tolerate that error, we're all good. However, there are some devices that don't, and so it could be that if I wanted to get 115 kilobaud and it gives me this kind of error, I might have to say, you know what, I can't do it. I need to slow down and run at 57,600 baud instead. So these are engineering decisions that have to be made. Now, one of the reasons why this might come into play is that for some devices or some applications, you need to run your main clock at 9 megahertz, and you don't have a choice. You can't run it at 12, you can't run at 15 for maybe power reasons. Maybe it's because one of the other devices that you're running inside of the LPC802 needs some combination of factors that requires the main frequency to be 9 megahertz. Anyway, as you put together your system, this will come to light, and so you end up having to make choices as to how much error you tolerate in your transmission. If we look over here, we go from this 9 megahertz value where these transmission frequencies result in no error to, say, down here at 15 megahertz, you'll see that only at 9600 do we get a baud rate error of 0, whereas it is non-zero for 14400, 57K, or 115K. All right, so that is an overview of the tables for baud rate. How do we actually run an example using the UART? Here we go. So we have the initial setup for our program. It's pretty standard. This is what we normally have. We have a main function. Inside of the main function, we have a couple of temporary variables. We also have a string array that's in 8-bit chunks, and that array contains A, B, C, D, E, and a null character. You'll notice that there are single quote marks around each one of those letters. All right. From there, we are going to disable the interrupts, and now we have to start feeding in our clock. So we have to choose a main clock. We're going to choose a main clock of 12 megahertz using the source of 24 megahertz, and the code for this is all pretty standard. You've seen this before. Next, we need to turn on the USART, and we're going to use USART 0. Remember, we're calling it USART 0 because that's the actual name of the part inside, but we're only using the UART component. We're not using the synchronization component of the USART, so it's really still just a UART. We are going to turn it on by clocking it. That's one of the things that we have to do on the ARM system. And then we have to reset it. Okay, so we're going to reset the module. Now we're ready to use it. In order to properly use it, we though have to engage the switch matrix to route the internal signals of the USART into the external pins on the LPC802. The table for the UART or USART and the switch matrix shows that if we're going to use USART 0, we want to use the transmit and the receive. Okay, so those are the bottom bits in pin assign 0. And we are going to use, I believe it's 0, GPIO 0, and GPIO 4. Okay, we're going to make those connections. Okay, from there to there. And this is how we do it. It's important to point out we're going to use PIO 4 and we're going to use PIO 0. PIO 0 is for receive. PIO 4 is for transmit. All right, so we're going to use the switch matrix. The switch matrix is going to use pin assignment. We're going to use the mask. We're going to zero out the masks for, or zero out the values using the masks for transmit and receive bits inside of the switch matrix pin assign 0. Then we're going to fill those bits with 4 and 0. 0 is going to go into the receive component of pin assign 0, and 4 is going to go in the transmit component. Then we turn off the switch matrix once we've actually made that pin assignment. All right, next up, we need to take our FRO and we need to route it into the USART, and we're going to do it through the FRG0 system. The FRG0 system has that divider register and that multiplier register that we were talking about earlier. All right, and this is how we pull that off. So let's say that we needed to set up a UART or USART clock. We're going to want to run at 300 baud. We know that the mult register needs to be 244 based on these tables that were set up earlier. The BRG value needs to be 1279. OSR by default needs to be F, and we're running the FRO at 12 megahertz. This will result in a baud rate error of 0. Okay, using that MATLAB script that I showed earlier. Okay, so now we're going to use the FRG as the input into the UART. Okay, so we need to feed that in there. Then we need to choose the FRO as the source for the FRG. And then from there, we need to set the divide and the multiplication registers for FRG to be F. And we need to, let's see, set 244 as your multiplication value. All right, from there, what do we have to do? We need to set BRG to 1279, and we're setting our OSR to 15. That we'll add a 1 to that, which gives us 16 as part of that equation that we saw earlier. All right, so we're now going to be shaping these packets. Now, what do we mean by shaping these packets? Well, what is that information that we're putting into the packets? Well, if you put your transmission line on a logic analyzer, you'll see that it will take individual zeros and ones and convert them into ASCII characters if you tell it that's how it's supposed to be interpreted. Okay, A will look like that, C will look like that, etc. If we're encoding these values from an ASCII perspective, which is a standard for representing alphanumeric characters, the A character is actually known numerically as 41, and it's represented as a 4 and a 1. Your B character is 42. This is capital B is 42, and it's represented as a 4 and a 2, like that. All right, so 4 and 2, 4 and 1. Let's take a look at how this works from a time sequence when it's actually being sent over that wire. All right, so we start off with a start bit. That start bit brings the transmission line down to 0. Then we put a 1 in there. Then we put a 0. Then we put another 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 0. Then we put a 1. Then we put a 0. Okay, and as you can see, this is 4. That's 4. It's basically 4 backwards. Okay, from sort of this visualization. Let's take, and then there's a stop bit. Okay, we have one stop bit, and that stop bit is a value of 1. So that whatever's interpreting the data, the 8 bits that are coming through, it knows that we're now done with those 8 bits. So it knows that there's a start, a go, and a stop. All right, let's do the same thing, but for the letter B. Okay, so we go. So this is the start bit, and that's a value of 0. Then we put a 0. Then we put a 1. Then we put a 0. Then we put another 0. All right, so this right here is the number 2. It's just spelled or written backwards in the logic analyzer. Then after that, we put another 0. We put another 0. We put a 1. We put a 0. And that is a 4. In this case, it looks backwards. Here's the 4 there, and there's your 4 right there. Okay. And then we have the stop bit, which is a value of 1. And that's how you transmit A and B using your USART over time. All right, how do we set that actually up? Here's how we do it. We tell the USART that we want to configure it. We want to have a data length of 8. We don't want any of this error checking, so no parity. And then we want to have one stop bit. You saw that stop bit in the animation. Don't worry about the control register. You want to set the status register to a bunch of Fs, so a bunch of bit 1s. So don't worry about that right there. And then what you need to do is you need to enable the USART. So you go configuration and you run the enable mask, which I believe is bit 1. You set bit 1 to 1, and now the USART or UART is ready to go. We then enable interrupts globally. We're not actually going to use any of these in the USART itself. The USART isn't being used in interrupt request mode. All right. Then inside of your main loop, what you want to do is send characters. How do you send characters? Well, you have a while loop like this, like that. And inside of the while loop, we have a do, and that do will increment through that array that we defined earlier. That array contains A, B, C, D, E, and a null. And that null is really important in order to signal that we've gotten to the end of the characters that we're interested in. It'll actually get used right there. All right, so we increment going from one value to the next, okay, like that, and then it begins again, like that. So while USART 0 status, so it's going to be checking the status of the USART, and this is important because you want to make sure that you only load it when it is ready. So you check its status, and you're checking to see that transmit, the transmit feature is ready to go. So it waits for transmit to be ready. Because what ends up happening is that you're taking data, you're putting it into the USART's transmit buffer, and then the USART will then take what's in its buffer and then transfer it out, sort of in that sequence of bits that you just saw happening, okay? And it can only be refilled when that buffer is completely empty. So then basically it waits until transmit's ready, and then it takes this temp value and puts it inside of the txdat or transmit data register. And once it's in there, it will automatically or automagically pop it out the electrical pin. Okay, and we'll keep doing that until it gets to that null character, at which point we start the process over again. We send another sequence of A, B, C, D, E. And that's it. So my recommendation to you right now is to actually try this out. Try to send out a sequence of characters from your LPC802 or your LPC804. Send it out to the debugger. And that debugger will then take the USB line and use it to send information to your laptop, where you have a program like CoolTerm or RealTerm ready to receive transmission at, say, 300 baud or 9600 baud or 115 kilobaud. All right, good luck, everyone. Enjoy your experiments.